So the armature current here in this case is negative, but the field current is positive. This is the characteristics when we will be operating a separately excited motor. And this will also be the case for series motor during regenerative braking. So the arrangements for regenerative braking are shown in the figure. So the motor acts as the generator and develops an induced voltage EG. So EG must be greater than the supplied voltage VA. So you see over here, when the power supply VA is greater than EG, we will see that the machine is operating under motoring condition. So this is the case. So VA is greater than EG. So VA minus IARA is equal to EB. It should not be EG, rather it should be EB. So that is equal to K1 N5 So again, in case of phi, we can replace this as K1 into IF. So this is the basic motoring equation of a separately excited DC motor, where the field circuit is separate and the armature circuit is also separate. So they are separate from each other. So now what happens? During braking, the torque tau, that is equal to, let us say this is K3 phi Ia. So the field current in this particular case, it is constant, it is not variable, because the field circuit is separated. So K3, and this constant we have taken as K1 Ia. So what happens? Suppose you have a rotor. It is a rotating part of the machine which is driving, or rather which is moving in the, say, clockwise direction with a speed of n1. It is moving in the clockwise direction with the speed of n1. So what will be the direction of the torque? The torque will also be in the clockwise direction, say tau 1. So the torque should be reversed. So if the torque is in the clockwise direction, in the next moment it has to turn in the anti-clockwise direction. which is given by tau 2. So initially it is equal to tau 1, which is equal to k3 k1 IA. Finally, suppose it is reversing its direction of rotation, and it is equal to tau 2 is equal to minus k1 k3 IA. So the reversal in the direction of the torque, it should be minus tau 2, and this minus will go in this particular side. So you see, I can write this as tau 2 is equal to k3 k1 minus of IA. So that means during regenerative braking, your EB, or the back EMF, should be greater than VA, or the applied voltage. Your EB should be greater than VA. Right? So if your EB is greater than VA, so this direction, or rather this equation will change. So now the equation will be EB minus IARA is equal to VA. So this equation and this equation are opposite, because the mode of operation has shifted from the motoring operation to regenerating operation, or rather regenerative braking operation. That is the first thing that has to be understood or kept in mind. So now I can write this as EB from here, EB which is equal to again K1 N phi it is equal to VA plus IAR. So N is equal to VA plus IAR by K1 K2 IF. So you see, if you compare these two equations, the direction of the current has got reversed. So as the direction of the current has got reversed, there will always be a reversal of power flow. There will always be a reversal of power flow. So let me clear all these things. So during motoring, the power flow is in particular direction in this particular case. If we consider the series motor, the field circuit and the armature circuit are in series with each other. Here also the power flow is in this particular direction. But if you see the process during regenerative braking, there is a reversal in the direction of current. So it will be in this particular direction. So there is a change in, or the transition is in shifting of the current from plus IA to minus IA. But if you see the field current in this particular case, the field current remains as it is. It is always plus IF because you have not changed the field circuit. So the direction of the field current is this one. So what about the torque? So the torque changes from plus tau to minus tau because why? Because in order to attain braking operation, the rotor has to exert an opposite force so that the system slows down. So suppose I've already explained this to you. If you have a train like this, which is moving on the track, so suppose this is the motor M1 which is coupled to wheel 1 and this is the motor M2 which is coupled on wheel 2. So in both the cases the torque is in this particular direction. Let us say that the torques are same tau and this one is also tau. And what is the motion? This is the direction of the motion. What is the direction of the speed or rotation? It is in this particular direction. But when the braking or the brakes is applied and the power is returned, so the torque will shift from clockwise to anti-clockwise. So now the new direction of the torque is this particular direction. So if the velocity of the train is v1 initially, now it is changed to v2, but v2 is less than v1. Am I correct? So now, as the speed changes from v1 to v2, so the torque has got reversed. But an important point of observation is the speed. We have observed the field current, we have observed the torque, we have observed the armature current. But what about speed? We have to analyze that what is the direction of rotation first. What about the speed? That we have to assess or analyze. So let us analyze the speed. So now, what will be the speed equation? I will write this again. It is k1 n phi. It is equal to VA plus IA RA. So N is equal to, during braking, it is VA plus IARA divided by K1 IF. So IF is constant, so you need not bother about the denominator. So this is the speed during braking. Let us denote it by NB, where NB is the braking speed. So we have to calculate the speed during motoring. So the speed during is motoring, it is K1 K2 IF into N is equal to VA minus IARA. And let the motoring speed be Nm. So it should be, so Nm should be equal to VA minus IARA by K1 K2 IF. right? So what was NB? I wrote it, but for comparison I will write it again. So NB is equal to VA plus IARA by K1, K2, IF. So you see, if you compare the motoring speed and the braking speed, you see that there is a sign change over here. So from positive it has turned to be negative because the armature current has got reversed. But what about NM? If you see the numerator, VA plus IARA will always be positive. During motoring,
So as you can see that if we compare the two speeds, that is the, rather I would rename it as NG and NM, that is the generating speed and the motoring speed. So if we name this like this, so you see that the sign of NG and NM, they are same. That means their directions are unchanged. The directions didn't change, so your torque has got reversed, your speed direction has got unchanged, your armature current has got reversed, your field current is unchanged. So rather, this is very important, which indicates that the power is returned to the supply. The power has been returned back to the supply. So this is the characteristic feature of regenerative braking. Now this is one analysis. Another analysis is that if we see the quadrant based operation, so in the x axis we have torque, y axis we have speed, or rather you can, instead of n, you can represent it by omega also, plus omega and minus omega. So during motoring it was in the first quadrant because both on speed torques were positive, but during braking or the regenerative braking you can see that your torque has got reversed. But what about your speed? Your speed is unchanged. So there is a shift from the first quadrant to second quadrant. So there is a change in operation from quadrant 1 to quadrant 2. This is very important. So obviously the operation shifts from forward motoring to forward braking. The operation shifts from forward motoring to forward braking. So these are the important points. The motor acts as a generator and develops an induced voltage Eg. During braking, Eg must be greater than the supply voltage Va. So these are the important or salient features which are there, which is being repeated. The armature current is negative, but the field current is positive. The kinetic energy of the motor is returned back to the supply. A series motor is usually connected as a self-excited generator. So the arrangements for regenerative braking are shown in this particular figure. So we have two figures. One is the separately excited motor and series motor. So these two are the cases. But here you see, since the field circuit is separated from the armature circuit, the direction of the field current is reversed. But what about armature, or rather when the armature and the field circuit are connected in series, in case of a series motor? So if you see the connection, this is the armature Ra, and this is the field, that is Rf. So when the power flow becomes reversed, so initially I will just mark it with a different color. So during motoring, your current was in this particular direction. Let us indicate by IAM. But if you see braking, which is IAB, it is reversed. And since the field circuit is in series with the armature circuit, the field current is also getting reversed, unfortunately, from plus IF to minus IF, which is not desirable. Your field current should remain unchanged. So in case of series motor, the alteration has been made in this particular part. So you see, there is a change in the direction of the terminal. It is connected in such a fashion. So during motoring, what is happening? The direction of current is like this. But during braking, what is happening? Let us observe. So the power flow reverses. Right? So if you see here, during braking operation, your current, the field current, flows from F1 to F2. and during motoring the connection was like this. So during motoring your direction is from F1 to F2. So if you do this modification during motoring and braking, the direction of the field current in the series motor will remain as it is, or it will be unchanged. So this is very important, that without any modification you cannot use series motor for regeneration purpose or regenerative braking. So a series motor is usually connected as a self-excited generator, because you see the field is in series with the armature, that's why, and the kinetic energy of the motor is returned back to the supply. So let us stop here for today. See you in the next lecture. Thank you.